Welcome to 5507. The topic is Analog IC Analysis and Design. There are 45 students. I last checked the Luminous. Last academic year, close to 50 students. It's considered large classes because for these classes, we are going to use the commercial electronic analysis and design software, the EDA2, Cadence. So we have limited license. We cannot accommodate too many students. Just forewarn, this module, tough. There is a lot of heavy requirement, including the homework assignment, project, and also in-depth understanding of some topic. So if you just take this module because of the recent popularity in IC design, I advise drop the module. Okay, I know a lot of you want to join IC design because there is attractive pay out there. There is a manpower shortage out there. I get approached by a lot of companies asking for available student recommendation. But to be frank, this field is tough. So unless you are really interested, drop it. Okay. In the last academic year, I've seen students take up this module, struggling. Okay, struggling, really struggling. Cannot understand the topic, cannot do the project. Final exam also didn't do well. So don't join this module because the pay is attractive out there. I know it is. But take this module because you are really interested. Otherwise, very difficult. Okay, very difficult. Now, unlike past academic year, we allow students to actually use. We allow students. Can you still hear me? Okay. We allow students to use free tool like LT-Spice. So actually, starting last academic year, we decided to introduce EDA because a lot of industry feedback saying that students graduate from NUS, they still have to re-pick up the commercial standard tool that people are using. So therefore, we decided to give students a sense of what is really going on. Okay, so imagine this module. You have to know about circuit knowledge. You have to know about system. You have to pick out the EDA tool. Their homework, their project, their final exam. So if this is still not sufficient to scare you away, I don't know what it is. Okay, so just mentally be prepared. Okay, so for my part, I will cover 6 topics, 6 lectures. So the first lecture, just to entice you, so it's not going to be very difficult. So I'll talk about CMOS process. So everybody talk about CMOS. So what is really process? What are the things that you can do? What is really out there? Okay? And then next lecture, we're going to teach you from the fundamental single transistor amplifier. Now for those who have taken the EE5507, this is probably some sort of refreshing your memory, but we are going to go more in depth, okay? But nevertheless, whatever you learn in 2027 is going to be useful. And the third topic lecture, we are going to look into reference. How do you generate reference? So in circuit design, very important thing is reference voltage. For example, ADC. How do you know that at certain voltage it is 1110? Because you have the fixed reference, right? How do you know that the circuit always functions as it is without change? The regulator output always 5 volt. How do you know? So you need to create an accurate reference. So usually it is a voltage reference. It could also be current reference. So in a lot of circuit, we need current source. So you need to be able to make sure that the current is accurate so that it doesn't matter what is the temperature out there, what is the process corner out there. Eventually your circuit, if you simulate, design it to consume only 1 milliampere, regardless of the condition change, it will always be 1 milliampere. Okay? You don't want the circuit, when you first designed it, 1 milliampere. After the customer use it, 10 milliampere. Okay? That will not be good. And then we start looking at the OTA design. Some of you probably wondering, isn't it op-amp, operational amplifier? Now, operational amplifier, op-amp, is commercial IC that people sell, okay? Very generic one. You can use it to build many, many circuits. They are very general purpose. General purpose, in short, means that any dummy can use. Any dummy can use means that they have to design the chip carefully so that no matter how you use it, it will somehow still work. Maybe your feedback factor is not accurate, it's still stable, it doesn't oscillate, right? So in general purpose, you can do it, but you sacrifice a lot of things. And also it can drive any resistance that you want, even you use 100 ohm, it works. But the good thing about IC design is that you customize your own operational amplifier, but you don't have to deal with very low resistance, which means a lot of time, the buffer stage is not needed. You only need to drive capacitor, which is infinite impedance at DC. So therefore, it doesn't consume a lot of current. Therefore, we call it operational transconductance amplifier. So usually, the output have a very high output resistance. It drives the current, so we call it operational transconductance amplifier. So when you build a filter, you build any amplifier, usually when you talk about IC design, we eliminate the buffer stage to save the power, and we mainly deal with capacitor, so it doesn't draw a lot of current. And this kind of thing, we don't call it operational amplifier. We call it OTA, operational transconductance amplifier. So we'll talk about DC analysis. Okay, in short, analysis and design, they are reversed. So if we teach you how to analyze, you should be able to do the design. I forgot to introduce myself. You know my name? Just go back. So I'm your first lecturer, Chun Huat. I'm with EC department for many years, since 2004. I graduated from here, NUS, undergraduate, and then I go overseas for my PhD. My contact email, ELEHCH, any issue with this topic, this module, just email me. I didn't put down my phone, but it will not be difficult to find my contact number. Okay, 65161628. I don't give you my handphone. That will be too much. I cannot write. There's no battery. Just now I still can write. Why? No, forget about it. 65161628. Okay. You can also drop by my office. I strongly discourage that, especially under COVID. Okay, don't drop by my office, but you really think that will help you, email me first. Okay, we can make an appointment. Safe distancing still need to be obeyed. You need to show me the green pass before I allow you into my office. If you don't like my face, call me. If you don't like my voice, email me. Okay, so this is my contact information. Now, after the OTA, DC analysis, we move on to AC analysis. Of course, op-amp design, the important thing, or OTA design, the important thing is gain. We need to look at how much gain we can get. Also, bandwidth. What is the bandwidth for the OTA so that we can design the filter, the amplifier accordingly. And finally, for OTA design, this is graduate level, so we'll look at some sort of more advanced high-performance op-amp topology. Okay, so on and so forth. So this is the syllabus. So outline for this lecture. Okay, so I'll briefly talk about what is the requirement of this module, but this lecture we mainly will talk about CMOS technology, which is probably the dominant process nowadays. There are other variants. For example, recently more popular one, they call it RF CMOS or RF MOS. So that is very popular because they are able to implement switch that is very good for RF frequency or RF application. And there are HBT, process or Seagate BiCMOS process, which combine CMOS and also the bipolar junction transistor. But if you look at the market, so dominantly they are CMOS process. And the famous foundry, if you are interested in IC design, you should know. Nowadays, which are the foundry that dominate the market? TSMC, yes. How much percentage they are taking the market share? 70%. Is that much? I thought it's around 50, 60, but still quite a lot. Okay, they are far away leading other competitor. Okay, in terms of market share. So to be frank, they are the only one making the money. Okay, of course nowadays there are a lot of silicon shortage. So other company or other foundry are also making money. But other foundry will not die. Do you know why? Why other foundry will not die? Because customer will not let them die. Otherwise, they will be held hostage by TSMC, right? So if there is no alternative, let's say Samsung, 5 nanometer, then TSMC can ask whatever price they want because they are the only player. So other customer, no matter what, even other foundry process could be poorer, but they will still try to give some order in order to let them hang in there, survive. So in semiconductor, it's very important that you don't just have one supplier. You always look for the backup supplier, okay? So that your production line will not get disrupted. Okay, this is very important. Now, we will briefly talk about process option. So, of course, CMOS is popular mainly because of digital. But digital, they don't care about any other device. They only care about transistor. Because they only need to build logic gate, which is transistor, right? So, but for mixed signal circuit, for RF circuit, we need other component. We need resistor, we need capacitor, we need inductor. So we will look at other process option, okay? And then we will talk about passive devices, active devices. And in IC design, a very important concept is called matching. Matching. How do you create devices that are matching to each other? Why matching is so important, we'll talk about that later. And then finally, we'll briefly touch on the modeling. So modeling, we will not spend a lot of time because to be frank, I assume all of you have EE background. Who doesn't have EE background? Anyone? Okay, good. If you are of EE background, you should have learned devices already. Transistor, BJT, MOSFET, you should know. So you should know some fundamental about the model that people use for BJT and MOSFET. So we'll touch on that. So this is the weightage. For my part, I will give out 3 homework assignments. The homework assignment required EDA, cadence. I'm going to conduct workshop, cadence workshop, during the weekend. Okay, during the weekend. So the first submission will be happen at 31st January, Chinese New Year Eve. That is the first submission. No lecture, but you still need to submit the homework. So I already uploaded the homework. So if you quickly do it, you can enjoy your Chinese New Year. If you wait until Chinese New Year Eve, then that's it, your reunion dinner. Okay? You have to spend time on the reunion dinner table working on the homework assignment. So try to do it as soon as possible. But if you work out the schedule, 31st submission, today is 10, we only have 21 days, 3 weeks. And I don't assume any knowledge with you in terms of EDA, so I have to conduct workshop. So bring you up to speed, how to launch cadence, how to run it. Okay? So I prefer to conduct the workshop this coming Saturday. I will set up the schedule. I cannot conduct all the workshop at one go for all students. I'll split the student into 2 groups. So the first group will be 1 to 3, second group 3 to 5. In fact, the workshop material I have also uploaded in the folder called Manual and Model. Okay? I even have the file set up. So even you don't do anything, you download the file, set it up, everything is there. You can run it. You don't have to create anything. But it's better that you try to follow the step, create your own. Because subsequently, you need the skill set to do your homework assignment, to do your project. Okay? So there are, some of you might be thinking, this is straightforward, you have done that. But there are a few things that we add in. Because we are using the PDK, so we can now run process corner. So you need to know how to run process corner. So different transistor process, how would the performance be affected? The amazing thing about circuit design is that, if you think about that, despite the temperature variation, 25 degree to 100 degree, despite the process corner, fast, fast, slow, 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 fast, fast, slow, despite the voltage supply variation, the circuit works. That is the amazing thing. Why? Why? We will talk about this a little bit when we go to the lecture. Okay? So a lot of time when you run this process corner, temperature or the supply voltage, what you want to make sure is that the chip variation, regardless of how it varies, the circuit still works. Okay, to a certain extent. Because IC design is a very expensive process. You don't want to tap out the chip, coming back, it doesn't meet your spec. Do what? Tap out again. No. So you run very detailed simulation, make sure that it can work all over the different process corner, and then you tap out. Your chances of success have to be at least 99%, so you don't waste the money. Okay? So very detailed simulation is needed. So in this module, you are going to experience how to set up the process corner and run the simulation. Okay? Another thing, when we design the op-amp, a very important concept is called stability, phase margin. Now, if you don't go through the conventional, the standard way, if you go through the standard analysis, people just say loop gain and do the simulation, so on and so forth, and then try to find the phase margin. There are typical ways that people can do. But EDA2 has advanced so much. So they have introduced components that allow you to do all this stability analysis in a very simple manner. Even with the feedback configuration built inside. You don't have to break the loop. In the past, it's very tedious. You have to look at the open loop, look at the feedback factor, create the circuit, make sure phase margin is good. Sometimes that is not the true representation because you don't see the correct loading. But nowadays, the tools are so advanced, you don't have to do all this. The inverting amplifier is exactly the inverting amplifier. Although you set up the inverting amplifier, you just have to insert something, you can do the stability analysis. Okay, so these are the things that we need you to experience. Another important thing, Monte Carlo simulation. Monte Carlo, you know, is statistic, right? So why do we need Monte Carlo mismatch? When we build the op-amp, a lot of time we are struggling with one thing, offset. Right? The op-amp that we built has offset. So how do we minimize the offset? How do you know that the chip come out will have this kind of offset? We need to predict, as I mentioned. You need to be able to predict it before even the chip coming back. How did people do that? They built all these process variation into the model. And then you can actually launch the Monte Carlo simulation, and they will try to see how will the offset voltage vary. So the EDA workshop simulation will show you how to do all these things. So this coming Saturday, we are going to set up. I already forward your name, user ID to EITU. They will set up the account. Once the account is ready, I will send you the PDF. What I require you to do before you come to the workshop is that you are able to access the EITU workstation. There are documents telling you how to do that. So what kind of document? EITU, remote access to EITU workstation. So you have detailed instruction. You need to install Xmin. You need to install some PUTTY. Okay, my personal usage, I don't use PUTTY. I use the WSL, Windows Subsystem Linux. And then I install Ubuntu. I can access, but I still need the Xmin. Okay, so you have this detailed instruction how to launch the VPN and then access the EITU workstation. using a username and user account and password, and then how to launch the virtual show. Okay, if you are very ambitious, you could even follow the Cadence workshop. Okay, they are too far. This is Cadence workshop. Another one is actually about offset voltage simulation. These two. You can even go through yourself. I have step-by-step instruction. I capture the window. So if you see this window, what to do. If you see that window, what to do. Everything is there. You are in this class? Just come in. Okay? So you don't have to wait until Saturday, and if you are really familiar, you don't have to join. Workshop, you don't have to join. But if you are not familiar, please join. Because your homework assignment, your project, all required EDA. Okay? I hope after this module, at least you know what is going on. What is IC design? Not just the theoretical analysis. You have experienced how to use the tool, how to run this simple simulation, okay? How to plot the result, so on and so forth. Okay? Now, assignment 20%, project 40%. Now, this is a 2-lecturer module, so I'm in charge of the first half. So my part assignment will be 10%. My project will be 20%. Now, this academic year, we decided to increase the project and assignment because your senior feedback, they spend too much time on project and homework, which is understandable because they need to use a lot of EDA too. Okay? So we decided to up the weightage, and then we try to reduce the final exam. So if you are confident, you say, oh, already assignment project got 60% already. I don't turn out for exam, and you can still pass. Okay? It's very strange that I fail you if you got 60 marks. So if you are very confident, you already got 60% of assignment and project, fine. You don't have to attend the final exam. This is recorded, I shouldn't say that. Okay, you should still come for the exam, but you know what I mean. Now, project, for my part, I'll give you some spec about the project. So my part is about OM design, so the OTA design. I'll specify you need to design OTA to achieve certain gain, to achieve certain GBW, to achieve certain offset voltage. So you need to come up with a design that are able to do so. And then you need to prove your design using simulation. Okay? Your simulation need to be very clear. Now what do I mean by clear? What I found out from last AY, academic year, is that I expect students to know what I mean. So I just write the homework assignment, provide simulation file, and all sort of things turns up, which make my life miserable. So this academic year, I decided to give very specific instruction for the homework. You need to do this, do this, do this, get this, get this, get this, and finally do what? If you fail to do any of this, 0 mark. Okay? So for the project, if you go through the homework assignment, you will know what I mean. What is needed to be shown. Okay, what is needed to be shown? Usually, transistor, we expect transistor to operate in saturation region. So you need to show schematic. Every transistor, the VDS is bigger than VDSF. You need to show that. Okay, so prove that transistor is in saturation region. Now, if you are talking about the gain, you need to give me the dB. You need to give me the GBW. If you are talking about phase margin, you need to plot the amplitude and also the phase. Show that at 0 dB, the phase margin is 60 degrees, so on and so forth. Okay? So what to do, what to expect. This is very important. When you join the industry, your manager asks you, please design this circuit. You don't just tell your manager, oh, I completed the design, it works. They expect you to show something. If you are design op-amp, they will give you the spec, 60 dB. Do you meet it? All the process corner? Okay, you need to make sure at least above 60 dB, under the worst case corner. Okay, so on and so forth. So this is tough. We are trying to mimic the industry situation. So not exactly, I think industry will be even more stringent, but at least you get the taste of it. Have I scared you enough? Do I still expect to see you next week? Okay. Then in your project, You cannot just say, I got the schematic, I got the design, my job is done. Okay? What I don't want student is to come back to me, sir, this is the simulation result. It works. So if you are in the IC design industry, usually there is the so-called process design review. Design review. So it is a team project. So the team member in charge of, let's say, OTA design, they will go out there. They will say, okay, in terms of folded cascode, telescopic, two-stage, I decided to pick folded. Why? As planned. Right? Because dominant pole, very easy to compensate. Okay? I pick telescopic. Why? Because I don't really care about the range. The range, I don't need to be very a lot. But telescopic, very, very power efficient. Justification. Reasoning. Okay? Convince people you pick the right design. For compensation, as planned. Why do I use Mueller compensation? Why I didn't use the pole zero compensation? Okay, what is the reasoning? As planned. And then how do you arrive at the calculation? Why eventually I pick a capacitor of 1 picofarad, not 5? Okay, so don't just show your design saying, this is the schematic, it worked. This is the really lousy designer. You have to be able to stand on the ground, defend your choice. Okay? Now, we are using the GPDK. G stands for generic. This is the PDK given by Cadence for teaching purpose. It's not real. It's not real. But the good thing is that it's almost like a real process, except that you cannot use it to tape out. But it will be very similar to, let's say, TSMC, 45 nanometer, UMC, 45 nanometer. So you see the same thing. They will model the process corner. They will model the Monte Carlo statistical variation. You can even use it for the layout. To be frank, I would really want to do the layout. But I think you guys will go crazy. So I decided to only stop at the schematic simulation. I will see, maybe your junior will suffer. So you guys get off the hook. But with this GPDK, you can really do a lot. Okay? You'll get to learn all these process and two feature. Now, let's come back to the official business. Let's go through the topic. I myself is analog and RF designer. In the past, there's always this debate. If you're IC designer, you always face this dilemma. Do I go to digital designer? Or do I go to mixed signal designer? Or do I go to RF designer? Right? There's always this struggling. So during my time, it's already like that. Even now, also the same thing. But to be frank, if you really want to good at IC design, you don't classify yourself as pure RF, mixed signal, or digital designer. You need to learn a little bit. So it is like you need to cover all these three, but pick one that is more in-depth. So when people talk about digital design, you know, oh, I can use Verilog. I can code simple Verilog. I don't have to rely on somebody. I can do some simple synthesis. Okay, as long as it's not critical. You ask me to synthesize MCU, I probably give up. But you ask me to synthesize SPI, serial peripheral register, I can do it. You ask me to synthesize delta sigma modulator, no issue, I can do it. Right? So these are the things that we expect. So you don't want to classify yourself as pure analog designer, which you can only design amplifier, mixer. That is not good. You need to be more versatile. You know what is going on out there, even though you're not expert. But you have expert in the domain. Other thing, you know a little bit. Now, when I study IC design, I used to be facing this issue. I see that digital is encroaching the analog and RF area. They are getting more and more there. Analog seems to be losing out. Okay, why? Because digital, if you think carefully, they have a lot of attractiveness. You only deal with 1 and 0. You can store the value. More importantly, you can program. right? If you want the digital filter, change the coefficient, different digital filter come out. Okay, so digital have a lot of attractiveness. And of course, it doesn't help. Nowadays we have AI. Everything is digital, right? So it used to be, we see the chip, more and more people try to make them digital. And the analog seems to be losing ground. But to be frank, they will not disappear. Why? Because we don't live in Matrix. The recent movie, Matrix Revolution. You see the world, you don't see 1 and 0 dropping down. Right? You don't see that. I see you as a person. You have contour. Analog contour. Your hair, I can see the jagged line out there. I don't see like this kind of staircase of your contour. It doesn't happen like that way. So the world is analog. So yes, digital is attractive, but if you need to somehow interact with the external world, analog and RF still needed. So transceiver, you need to talk to the base station, you need carrier wave. How to do that? You need antenna. How to send to the antenna? You need power amplifier. So that is still analog or RF. You cannot get rid of that, although they try. Okay, they try. So you don't have to be too worried that eventually everything is digital. Now, I remember there is one professor from Stanford sharing this story with us. He's saying he was approached by, do you guys still know what is Nokia? Have you heard of the company called Nokia? Long time ago, they dominate the digital cell phone, right? Mobile phone. So they were approached by Nokia. Nokia overtake Motorola. Motorola used to be the winner in terms of analog cell phone. Nokia take over, right? So when Nokia approached that professor, he's asking him, are you able to design a cell phone, an ADC, that right away the RF signal digitize, and then give you the digital output? Get rid of what? Amplifier, mixer, filter, everything. So after the antenna come in, ADC. Why this is attractive? Because after ADC, everything is digital. I just need to program it. I have processor, ARM processor, very powerful. I have GPU, I can do everything. The professor answer is, yes, I can do it. If you give me budget, let's say 100 watt. Because in order to do that, your ADC is going to be very power hungry. The signal you will try to digitize is at 2 gig, at 3 gig. So Nyquist rate tells you, you need sampling rate of 5 gig, 6 gig, right? Of course, you can adopt something called subsampling. But subsampling concept introduces a lot of noise, right? So the performance will not be good. So no matter what, analog is still there, okay? Now, the digital guy might be very proud saying that, oh, digital is very easy. I just program, Verilog coding, VHDL. And then Synopsys help me do the synthesis. Cadence, Encounter help me, no, it's not called Encounter, there's another name. Help me do the place and route. And then I just push a button, the chip come out nicely. I don't have to do anything. And you guys, analog designer, only design 1,000 transistor and you are already screaming, digital designer design million transistor. No problem, right? But that is when you are talking about simple system. If you are talking about very high performance system, let's say the clock speed is really, really advanced, tens of gigahertz, you don't have much margin. You really have to sit back and think, is the logic gate that used by the library good enough? The standard digital cell library, NOR gate, AND gate, is it good enough? How can I squeeze the speed? Let's say the standard process can only give me operation up to 1 gig. But my boss is ridiculous. Ask me to design a digital circuit that can operate at 5 gig. What can I do? Can I just do a simple thing, digital standard cell, and if cannot do, I tell the boss I cannot do? Or do I have to sit back and think, what entice or what contribute to a high-speed digital design? Maybe I have to design the digital cell like this. like this. Okay, this doesn't look like digital cell, but it's actually digital cell, current mode logic. Okay, how it can run faster, if you think carefully, digital logic run from 0 to VDD. VDD is 1, 0 is ground. But current mode logic try to shorten the level. So let's say VDD, but I only make sure the current logic switch between 0.8 VDD and VDD. 0.8 VDD is low, VDD is high. So imagine, you need to run from here all the way to the top. Take a long time. But you run here up to that staircase, 4 staircases away, you finish the journey much faster. But can you differentiate 1 and 0? Of course. Standing there and standing there, there is a difference, clear difference. 1 and 0, you can differentiate. Right? So not only that, a lot of time when you think about digital design, let's say I want to squeeze the setup time a little bit more, you have to start thinking, can I embed this logic inside the logic, another logic, so that to eliminate certain delay. So even digital designer, if you think carefully, if you really want to be very good, you have to start understanding circuit in the analog way. Okay, so what I'm trying to tell you is that there is no clear-cut digital do programming, analog do circuit design. Okay, so analog, you still need to understand digital. Why? Nowadays, we like programmability. When you design filter, you want the cutoff frequency to be able to change. You want the amplifier gain to be able to change, right? Change in how many dB per step. So all this requires some digital knowledge. So you can see that do you know the famous China symbol? Tai Chi, yeah. Right? A big white have a small black. A big black have a small white. So if you think carefully, it's like that. Analog design have some sort of digital element. A digital design has some sort of analog element. Right? And that makes a perfect world. Okay? So here, you can see why digital is dominant. So digital only require what thing? You only require MOS transistor and layer of metal, right? You just need to connect one transistor to the other. So the more metal, you can make the design more compact. Now, analog require a little bit more. Beside the transistor and the metal connection, it requires resistor. So there are different kinds. There are N-wall resistor, poly resistor. They also require capacitor. Here I show min cap. Later you can see there is also mom cap. Now RF require even more. So beside the typical resistor and capacitor, you also require varactor, which is a variable capacitor. This is very important in terms of tunable filter cutoff, tunable VCO frequency. Okay, so because you can change the capacitor, you can change the frequency. Spiral inductor, you want to build the inductor yourself so that you have the resonator and you can create RF oscillator. Okay, so there is the RF process. Now, founding process, there are other founding process. EEPROM, electrical erasable read-only memory. So you can select, if this process includes this guy, you can actually build on chip memory and it's programmable. That is very attractive. Let's say you come up with MCU and then you want to store some bootable ROM inside the chip so that the MCU can read the bootable ROM and the whole chip can run by its own. Okay, and every time you want to update the ROM, you just have to erase whatever inside the ROM, update it with the new content. Okay, so this is expensive, so not all the process, generic process don't include it. You have to request and pay a little bit more. Non-silicide and silicide process. So silicide, you try to make the resistor higher resistance. Okay, non-silicide, sorry, should be the other way. Non-silicide will make the resistor higher. Okay, silicide, you try to make the contact with the semiconductor so the resistance can be lower. Okay, so this kind of process allows you to achieve high resistance. Using silicide, you can still get high resistance, but it's going to take a lot of area. Okay, but with non-silicide, because you can get higher resistance per unit area, so therefore you can get very large resistance with very small area, which is attractive. Now MEMS. So if you think carefully, MEMS actually, it sounds very exotic, but if you really look at it, it sort of involves packaging and metal. So you design different metal structure, so they sort of produce some sort of mechanical resonance out of it, and that is what people make the MEMS of. Okay, so simply put, it's just a metal structure in a different way so that you can create resonance behavior. CMOS image sensor. Before CMOS image sensor come along, when I first started up, I think the popular image device is called CCD, charge coupled devices. So nowadays, the high-end image sensor, they still use CCD because it can produce very low noise image. But most of the cell phones nowadays, they are using CMOS image sensor. The quality is not good. The good thing is that we have image processing. So although the taken image is not good, but you can do all sorts of processing, average out, lower the noise, okay? Or enhance something, eliminate something, cancel something. All these things can be done using digital processor. So nowadays, most of the cell phone will be using the CMOS image sensor. Now, double poly capacitor, that is a very old time. It's no longer popular. So used to be when we want to make a lot of capacitor, so by having the double poly, the good thing is that the top we can have min cap, at the bottom we can have poly cap. But you look from the top, they occupy the same area. You get twice the capacitance, right? But the bad thing is that poly, because they are at lower level, they have a lot of parasitic. Okay, so this parasitic is not attractive. So nowadays, advanced process don't use it anymore. But advanced process nowadays, you see this thing, low threshold devices or super low threshold devices. And in fact, from 19 nanometer onward, you see this thing. The foundries start to separate the process into two. One is called high speed, high performance. Another is called low power. So what is high performance? High performance, you want to be the transistor to have larger current, the logic gate run faster, so high performance. What do? You lower the threshold voltage. By lowering the threshold voltage, so just using the square law, VGS minus VTH, the whole thing squared. Because VTH get lower, your VGS minus VTH get a lot bigger. So the current get a lot bigger. So that is how you make larger current driving capability and the circuit can run faster. Then somebody don't like. They say, I don't require high performance. I don't want to score 100 mark. 60 mark good enough already. Because I only have to spend 1 hour per week. If I want to score 100 mark, I have to spend 10 hours per week. I don't want to do that. That is high performance mode, right? I want low power mode. I only consume 1 hour per week on this module. So if you want to do that, you can use high threshold. By using high threshold, you draw very little current. Okay, so it cannot run fast, but doesn't matter. A lot of time, the MCU you use for IoT, they don't run at gigahertz. They run at 10 of kilohertz, 100 of kilohertz. That is good enough. Okay, so different threshold devices. Thick gate devices, this is more for the I/O. Because of historical reason, the IC design has been developing, starting from 3.5 volt, 6 volt, go to 3.3 volt, and then go down to 1.8, 2.5, 1.8, 1.2, now is 0.9 or even 0.8, right? The supply voltage keep lowering. But you will still have some legacy there. So let's say you design a new chip, but somehow the new chip have to talk to the old chip. Okay, you cannot say, oh, my grandparent is old, I don't care, I don't talk to her. Right? I don't talk to them. That is not good. Right? You still need to talk to that guy. That guy can still function, so why replace them, right? So therefore, you have to incorporate some tick gate devices inside your current process so that you are able to generate 3.3 volt, talk to the old guy. You are able to generate 5 volt, talk to the old guy. Okay? Not only that, a lot of process require high voltage. High voltage. For example, automotive application. Okay? Even the display, your display driver require high voltage. So tick gate will help because with thicker gate, it can handle higher breakdown voltage. And there is other process choice I mentioned just now, bi-CMOS. Not only they give you the CMOS device, they also give you the bipolar devices. Or pure BJT, nowadays very rare. Okay? More popular is like HBT. Okay? Heterojunction bipolar transistor. That is some unique application. Let's say satellite application, millimeter wave application. So people require device that are more exotic and high performance. And of course, 3,5 gallium arsenide and indium phosphide. So there are all these different processes, but CMOS is still dominating. So let's take a look. How do you actually design the component in the IC? So for those who, how many of you are IC designer? Any of you? Nobody? IC designer? Maybe. So I can smoke you. I can say anything I like and you don't understand whether I'm correct or wrong. Because no IC designer here. Okay, anyway. If you are doing the IC design, you will know. IC designer have to do the layout. Of course, in big company, they don't do that. They have special designer doing the layout. The designer just design the circuit. Layout engineer do the layout. That is for big company. They separate. Now, they separate that because layout engineers are very efficient. They are very fast. They are so familiar with the command, they can complete the layout. Compared to the typical engineer, they probably can work on 3-4 projects together at one go. So they can support 3 or 4 circuit designers. Now, circuit designers know the layout, but they are not very efficient. Their time are better spent designing the circuit because they can think whether this circuit work or not, what need to be tweaked. So their time don't want to be spent on layout. So that's why they separate the role. I used to tell my students, if you get the help from the layout engineer, don't think that if thing doesn't work, you blame them. In company, it doesn't work that way. Layout engineer is helping you. If the circuit doesn't work, you are responsible. If you don't like the layout, tell the layout engineer. Okay? Because anything happen, not their fault, your fault. You are the one in charge. Okay? But usually they are quite experienced, so they've done so many designs, they know if differential amplifier, how should you lay out in certain way. Okay? To get a better matching, what you need to do. But even then, if something doesn't work, your responsibility, not them. So, as IC designer, we need to do the layout. The layout, what we do is actually doing the mask layout. So, for example, showing over here a passive device, how do you lay out a resistor? A resistor is a very simple device. If you think about resistor, it's just a piece of wire. If the wire have different resistivity, the longer the wire, the larger the resistance, right? But if you use metal wire, that is not good for resistance because metal have very small resistivity. So what do you need to do? You can use semiconductor. Semiconductor is semiconducting. So the resistance is higher. And you can control the resistivity. How do you control? Whether I dop the semiconductor, make it high conductivity, or I non-silicide, I don't do anything. I block the doping. I don't dope anything. So high resistivity. Okay? So how do you determine that? You lay out the mask. So for example, here I show a silicide block. I draw a rectangle. So at the middle, actually I don't show the transparent thing, but you can see that the wire actually go through all these things. The red color one is actually a piece of poly semiconductor. Okay? And the bigger rectangle, the silicide block, it will create a mask so that you don't have any implantation implant to the semiconductor. So that piece of poly is going to have high resistance. You still need to make the contact. So how do you do that? So you try to create a metal, and then you try to open up a window, so the metal will get direct contact to the poly, and then it will form a resistor. So there is cross-sectional, that is exactly what happened. The silicide block is going to create this mask, so it will block the implantation. So only this side will get high resistance, low resistance, sorry, because they have implantation. I should use different color. So only this side will get high resistance, low resistance, but this portion underneath it will get high resistance because it is being blocked, no implantation. But you need to make a contact to form a resistor. So you make a window opening here, and then you deposit the metal, and then you will form the contact. So IC designer looked at the circuit from the top, how to lay out the layer, how to do this geometry so that I can get the device that I want. But they need to understand how this thing translates to the real devices. Though they need to understand cross-sectional, what really happened. Okay? And there's a lot of design rule governing that. They will say the opening of the window cannot be too close to the silicide block. Your silicide block need to be much larger than your poly by how much? Right? So these are all the design rules. Why we need the design rule? Make sure that the chip come out will behave exactly as it is. Even there are some manufacturing variation. So these are design rules. Now, beside register, how about N-well register? N-well register is much simpler. Okay, you just have to create an N-well, and then you just have to make opening, do the implantation at the two ends, and then make a metal contact. That becomes a register. Okay, so the register is formed by the N-well. So this is the register. So this is the register, the N-well register. Now, poly register is good in the sense that it doesn't have voltage dependency. Just a piece of semiconductor, right? The bias voltage doesn't change anything. Now, the N-well is not that good because usually there are some voltage. This is ground. Now, this guy, you will connect to some voltage, let's say VDD. And then this guy, you will connect to some other voltage, let's say V1. Now, substrate is usually P-type. So N-well is N-type. So you're actually forming a PN diode. For PN diode to form, you have some depletion region. This depletion region will change based on the voltage. Now, when the depletion region changes, the voltage change. The voltage change, the depletion region change. Your depth of your N-well will change. That will vary your resistance. So this kind of N-well resistor, it will have voltage dependency. Okay? And you don't want your circuit, you basically, if you want to have 1K, you want the resistor to be always 1K despite whatever the voltage applied to it. Am I right? You need the resistor to be reliable. So this kind of resistor, if it have voltage dependency, meaning that it depends. If your circuit operates at 1 volt, you have this kind of resistor. If the circuit operates at 0.5 volt, you have different kind of resistor. Okay? For some application, it doesn't matter. Okay? Then why people use N-well? The resistivity usually is higher. Okay? And actually, there are some IC designer come to NUS, give a talk, from industry, they say that they prefer to use this kind of N-well resistor because the matching property is better. So they use it for ADC creation. So in ADC creation, the matching is better, so they can actually get good ADC out of it. So there are all sorts of reasons why people still use, although there are voltage dependency. So typical resistor value, it depends on the type. So if you have normal poly implant with electron, so N+, you get probably 4 ohm per square, okay? P+, 3 ohm per square. So it depends on the implantation type. And then N plus block, P plus block, basically you don't have any implantation. Block means blocking the implantation. You have much higher resistivity. So like 60 ohm per square, 170 ohm per square. And for N-well, you can see that you get about 1000 ohm per square. So the unit seems to be strange. Why is it called 4 ohm per square? I thought these things should work. Without the pen, it's very painful. Where is boy? Without the pen is really painful. Let me see, what can I do? Nothing I can do. Now, why the unit is ohm per square? Now you lay out the register like this. This is the top view. So let's go back to this register. This is the cross-sectional view. So if I draw the 3D, it will look something like this. So this is the 3D picture. Okay. This is the width. This is the length. And this is the thickness. So if you want to predict the register, it is called R equals to resistivity rho multiplied by the rank divided by the area, which is the W multiplied by the T. Right? So what this guy is doing is to make sure that they select the L to be the same as W, but use something called multiple. So I have an N multiplied by W, and then WT multiplied. And then the whole thing becomes rho W over WT multiplied by N. So this whole thing, if you work out the unit, it becomes resistance per square. Resistance per square. So how much resistance? It depends on how many square you want. So that's why the unit is so strange. 4 ohm per square, 3 ohm per square, 60 ohm per square. So here is the example given to you. Suppose I want a resistor that is 500 ohm, and I'm using N plus non-silicide resistor, so it's 60 ohm per square. So I need to have 500 ohm, so there is 60 ohm. I divide 60 ohm, divide 500 ohm by 60 ohm. I look at how many square do I have. How many square do I have? It turns out it requires 8 square and a fractional, 1/3. So to lay out the register, once you do the width, you determine the width already. Okay, you just do the same over here, so it becomes 1 square. So from the calculation, you need 8 square, so you just create 8 square nicely. And then the last one, 1/3. So the square, you just chop it into 3 sections, and then just take 1/3 of it. So that is how you form the register. So you can also form the register. Let's say now I do a bigger register. Okay, your square now is bigger. 4, 5, 6, so 7, 8. And then another 1/3. So these two registers, one has smaller area, one has larger area. They both give same resistance. Okay, they both give same resistance. So once you know how many ohm per square, you decide what width you want. And then you can calculate how many square. So you can get same resistor value, big one and small one. Okay? Can you scan this? Use your handphone to scan this QR code. And then go to the website. Done? Not done? Finish? And then go to the website. Do you see the question? Register your name. Are you able to log in? Are you able to log in? Do you see this right now? Have you? No? I see that some of you already answered, because otherwise I will not see the response. There seems to be a clear winner. For poly resistor with 50 ohm per square sheet resistance, to obtain two identical 500 ohm resistor, which of the following provide better matching? Meaning the two resistors match better. Match better. So one condition is 5 ohm, 50 ohm, 5 micron, 50 micron. Another option is 1 micron, 10 micron. Okay? So both, it means that the top one is both 5 micron, 50 micron. The second one, both of them, 1 micron, 10 micron. So which one will provide better matching? This is resonate with what I told you just now. When we have 50 ohm per square, you can create same resistor value, one with the smaller area, one with a larger area. So the question now is that if you are able to create resistor, one with bigger area, one with smaller area, which one gives you better matching? Which one will you go for? So here is the response. 88% thinks that is the first choice. 12% thinks that is the second choice. Is it true? Is it true? Which one provides better matching? I don't want you to raise the hand, so I use this poll so I can record down your response. Which one is the correct one? How come I cannot close this? So the correctness, 85%. The larger the area, the better the matching. That is the universal rule. Why that is the case? To understand this, that's why I don't have pen to draw. Now consider a square. So you have two same shape. You draw it, but when you fabricate the devices, you don't get a nice rectangle. What you get is, sorry, I should use different color. So there will be these checkered things. This checkered thing. This checkered thing at the edge. So same thing here, same thing here, same thing here, same thing here. This edge variation is the one that is causing the matching. You cannot guarantee the edge of one side exactly the same as the other side. Think of it like twin. Twins should be identical, am I right? Not all the twins. those twins that come from the same egg should be identical, right? Or embryo, whatever, right? They should be identical. But would they have the same number of hair? You go and count. Maybe one twin will have 1 million, the other have 1,000,001, right? Throughout the day, how can you guarantee they all have the same number of hair? You cannot. So these are the things that cause the variation. But if you are talking about a twin so big, you will not be able to notice the small variation. So if the thing is very big, the variation on the top is only very little, you hardly notice it. So the matching is better. Okay? But when you make the device very, very small, then all these jagged things get enlarged. They occupy a larger percentage. And that will cause mismatch, poorer matching. Okay? Then in that case, which area should I use? So if you actually look at the document of the process, they will tell you, if you want to achieve 1% matching, you need to lay out the device with certain area. The area need to be bigger than certain amount. So that is how you pick the area. Then in that case, you'll be saying, then what is the use of small area? Can I use 0.5 micron and 5 micron? Yes, there are applications that you don't need to care about matching. You only want to get single register. It can give you the register value. So why do you care about matching? Make as small as possible. So it doesn't occupy a lot of area. Okay? Now, capacitor, we have min cap and mom cap. So nowadays I see more popular use of mom cap. Min cap seems to be less and less popular. There are reasons. So when metal capacitor first come out, min cap is dominant. The reason is that the min cap give you much better quality capacitor and much higher density. Okay, you can get very high capacitance per unit area. But the problem with min cap, it requires additional process. So for example, usually in the process, we already have metal 4, metal 3. So these are the typical metal out there for routing. You don't care about accuracy. As long as the metal is there, they can make the connection. You are happy. But if you want to make a capacitor, you need additional special area, special layer. This layer is called capacitor metal. It's sandwiched between metal 4 and metal 3. It needs to be tightly controlled. So you need to be controlled tightly so that the thickness between the capacitor top metal and the metal 3 are very well controlled. Because of this additional layer, it is expensive. You need to create additional layer to fabricate the device. So it is expensive. Okay? But in terms of matching, this is actually quite good. Okay? The quality is also very good. Nowadays, more popular one is the so-called mom cap. Mom cap is very easy. You don't need any special process. Just use metal layer will do. So if you have metal layer 4, metal layer 3, you just create interdigited. Okay? So one of them have like this finger, go there. The other have another finger, insert in between. How the capacitor is being formed? So you know that between two metal, you have a cap, right? So that is how you form the mom cap. Okay, the mom cap. The good thing about mom cap is that how many layers of metal you can have how many capacitance. So you can have many metal layers. Unlike the min, you can only use in between the two, right? So the mom cap, you can easily create it. So it is cheap. Okay, but in order to get very high density, you need to use up all the layer of metal. That is the problem. If you use up all the layer of the metal, the bottom layer is closer to the substrate. It has higher parasitic. Unlike the min, I don't need all the metal layer. I only need the top two, because I can tightly control the metal spacing. So this capacitor can have very large capacitance, but it is far away from the substrate. It means the parasitic is smaller. Okay, so this is min cap and mom cap. So this capacitance used to be 1 femtofarad per micrometer square. Nowadays, I think they improved to probably 3 to 4 femtofarad per micrometer square. Technology advanced. Okay, the good thing about the unit capacitance is the higher it is, the smaller area needed. So take 20 picofarad for example. So if I want to create 20 picofarad, you use 20p divided by 1 femto. So that will require 20,000 micrometer square. And then you take the square, it will give you roughly 20,000. So about 100 micron by 100 micron, roughly there. Very big. But if you have 4 femtofarad per micrometer square, then this guy reduced to 50. So you only require 70 micron by 70 micron by 70 micron. So the area becomes smaller. Okay? Now, all these components out there, the foundry cannot guarantee the accuracy. So usually you can expect plus minus 20% variation. For example, they tell you 1 femtofarad, you could end up getting 0.8 femtofarad. So if you fabricate 20 pico, you might end up getting 16 pico. That is one direction. You could also end up bigger, 24 pico. So there is no guarantee what value you will be getting. The foundry already protect themselves, right? If you don't get 20 pico, don't blame me. Okay, I told you already, it varied plus minus 20%. Now it's amazing, right? 20% plus minus, the circuit still works. So why the circuit still work? If you have learned inverting amplifier, what is the gain of inverting amplifier? R2 over R1, right? Forgot already? Inverting amplifier minus R2 over R1. So the circuit gain depends on the ratio of the two resistors. It doesn't depend on the resistor value. It depends on the ratio of the two resistors. So that's why matching is so important. If I can get two resistors match very well, down to 1%, my gain accuracy down to 1%. I design gain of 20 dB, it will be 20 dB. Very little variation. So that is the reason why even a component value is not accurate. You can still get very good, accurate circuit performance. Okay? Now, spiral inductor, it looks like a mosquito coil, mosquito repellent coil. Okay? To make a coil or inductor, that is very easy, right? You just use a piece of metal wire, wrap around, you can form a coil. Once you have a coil, you have inductance, right? The reason is because when the metal flows through the coil, okay, you will enhance the magnetic field in one direction using right-hand thumb rule, right? So because of this magnetic field created, you have inductance. So even a single piece of metal wire, you have inductance, but not good. Inductance is low. So if you want high inductance, you use spiral. So a piece of metal wrapping around. So you just enhance the magnetic field in the same direction. So the inductance is higher. So that is how people create inductance. Okay? So it is very area intensive. For example, to get 10 nanohenry, you require 300 micron by 300 micron. Now, this might lost to you. 300 micron, very tiny. But you know, most complicated chip nowadays, let's say a transceiver, probably take less than 1 millimeter by 1 millimeter. Okay? Even with most advanced technology, let's say you just talk about transceiver itself, it could be less than 1 millimeter by 1 millimeter. 1 millimeter is 1,000 micron. Out of 1,000 micron, 300 micron is being used for the inductor. So that is actually very area intensive. Okay, it occupies a lot of area. So if possible, we try to avoid too many inductors in the circuit. But sometimes it cannot help. And usually, for good quality inductor, you need the thick metal on top. So the thick metal on top, usually the thickness is 2 to 3 micron, and it can be copper. The very top is aluminum, but usually copper is better. Because the rigidity is smaller, the Q is better. Okay? All other metal layer usually have very thin, only 1 micron or less than 1 micron. So they are not good for inductor. Okay? Varactor. Varactor look like a MOSFET. Actually, I should stop here. But before I stop, I should ask one more question. So you are still with the website, right? So let me go back and activate the second question, and then we can stop for a while, probably 15 minutes. Activate. Show the QR code here. Done? Okay, now I present. Do you see the question? Take some time and do the calculation. Nobody respond. Nobody click. There are 4 options. Which one? Any other option? Only 3 submission. 4. Only 4% participate. I got 40 plus students here. I should expect 40 at the bottom right. If there is no 40, we don't go for break. We stay here until I see 40. Do I have 40 students? 1, 2. Okay, we don't have 40, 38. I expect to see 38 here. Anyone not doing? You can tikam. Tikam means throw a dice. 1, 2, 3, 4. Throw a dice. Pick any number. This is not quiz. You will not be graded, so don't worry. I want to engage these two because I want to understand how well you guys understand my talk. Okay? So I come up with all these short questions just to see or evaluate whether you are just sitting there sleeping or sitting there listening. Five more. 5 more to go. 4 more. 3 more. It's like counting down. 3, 2. Okay, 36 students. So let's see. Correctness. Why? I also don't know why. Okay. You draw the capacitor. The capacitor area is COX multiplied by W squared. Because I specified it's a square shape. So if there is variation, you are going to have COX W plus delta W square. Agree? Now, if you want to see the mismatch, you divide by the nominal value, COX over W square. You do and calculate using approximation. We are going to see that the percentage variation is 2 delta W over W. Over there. Okay? That is for this capacitance. But there is only one. Now, the other can go exactly opposite. So let's assume the other guy is not positive 2 delta W. The other guy is actually negative 2 delta W. So one of them will be 1 minus this guy. The other will be 1 plus this guy. So that becomes 4 times, right? So you divide. I already tells you the etching uncertainty is about 0.4. Okay? If you calculate 320 divided by 50, what is the unit capacitance? So I think the value is 64 micron. And then therefore it's about 8 micron, right? So you have 8 micron over here. You multiply by 2. So that will give you 1%, right? But don't forget, you have one can go one direction, the other go the other direction. So the worst case you can expect is 2%. Make sense? It makes sense to me. Okay, we'll take a 15-minute break. We can come back at 7:50. Is that okay? 7:50? We resume at 7:50.
Recording stopped.
Should it be 20% rather than 2%?
Did I calculate the number wrongly? Okay, then my mistake. Let me see. Where am I? 0.4 divided by 8. Sorry, my mistake. 0.4 divided by 8. Oh yes, you are right. You are right. Sorry, my mistake. There is a unit there, but you get the idea. Okay? Anyway, this is to test your understanding. It proves that my understanding is not correct. But you know the calculation. The number is wrong, but the concept is correct. Okay? Thanks for pointing out. Okay, I just created a group for this upcoming Saturday workshop. Every group is about 23. You can go and sign up. One group is from 1 to 3 p.m., another from 3 to 5 p.m. I will send you the account set up once I got it. Okay, let's go back to the lecture. So we have covered many passive components. This is another one, varactor, variable capacitor. In fact, it is a MOSFET. MOSFET. So if you have studied the MOS devices, every MOS transistor, when they start the device description, they will tell you a MOS devices is a MOS capacitor. So you apply some voltage at the gate. You will try to inverse the layer underneath. So then once you inverse the layer underneath, you can start conducting. So it's a MOS capacitor. But this MOS capacitor device looks very similar to PMOS device. You can see that the device is being created using N-well on top of a P subscript. But there is one very key difference. The source and drain region are using what doping? The source and drain region are using what doping? N+. If you are talking about PMOS devices, it should be P+, right? So what is the difference? This varactor is so-called the accumulation mode MOSFET. So the reason why the typical PMOS device doesn't work is because the P plus source and drain, they will provide hole. So when you have accumulation mode, the electron coming from the N-well will form the underneath plate. So you have a capacitor. So that is how you get the capacitance here. But when you have PMOS device in strong inversion, the P plus source and drain will supply the channel. This channel will also form underneath. And you also have a metal plate. So therefore, you get back the capacitance under strong inversion here. So you have two big capacitors when the voltage is biasing at the lower end in the accumulation mode or the higher end when it's strong inversion mode. So that doesn't work. We don't want that kind of capacitor. We want the capacitor that can vary. Let's say originally high, and then just keep dropping, and stay there. And accumulation mode do that. Why? Because when you have M plus source and drain, when you go into strong inversion mode, you need PMOS, you need hole. But where does the hole come from? Nowhere. Because you only have M plus. We have abundance of electron. You have N-well, abundance of electron. But nowhere can there supply you the hole. So you will not be able to get the inversion underneath. So the capacitor now will become something like this. So there will be a capacitor here, and then there will be another capacitor to this guy, another capacitor to this guy. So when you have two capacitors in series, the capacitor becomes smaller. So that's why the capacitor dropped over here. So you have this continuous variation of capacitance value using this varactor, okay, varactor design. So think of it like you can use the voltage to vary the capacitance value. This is very useful. In RF circuit, we have VCO, voltage control oscillator. So voltage control oscillator, we are using LC to form the resonant tank. So the inductor and capacitor together, they will form the resonant frequency. So if you are able to vary the capacitor value, you can change the VCO frequency. Okay? How about filter? Same thing, filter. You are able to design a simple passive filter like this. But you change the capacitor, your low pass corner get varied. Okay? Passive device matching. So a lot of passive component, if you look at the value, terrible. Okay, register value, foundry only guarantee plus minus 20%. Capacitor value, they only guarantee plus minus 20%. Because it's very difficult to control accurately. They try to implant the device, sometimes slightly overdose, sometimes slightly underdose. So the registers can vary, plus minus 20%. That is already considered very good control, right? So if you design a circuit based on the absolute value, you are screwed. So in circuit, if you come out with a circuit that depends on the absolute value, you will not work in reality. But a lot of time, you will see the circuit, they don't depend on absolute value. A very clear-cut example, inverting amplifier gain. It depends on R2 over R1. So it's a ratio, register ratio. Although I cannot guarantee register value, I can guarantee register ratio very accurately. 1%. If it's not good enough, use bigger register, 0.1%. So the gain can still be accurately defined if you are talking about register ratio. Switch capacitor circuit. Switch capacitor circuit. Use switch capacitor to define the register. Okay? So they can form the register using switching capacitor to form a register. So if you combine the register and capacitor, so for example, to form a cutoff frequency, you see, you look at this guy, register vary plus minus 20%, capacitor plus minus 20%. What is your cutoff frequency? Plus minus 40%. You design 1 megahertz, you could end up 600K or 1.4 meg. That is terrible, right? But you can replace this guy using switch capacitor. Okay, something like that. This switch capacitor, this whole thing, can actually behave like a register. And the register value is related to the capacitor value and the time period. Time period is accurately controlled because all digital circuit, you need an accurate clock. So the clock is accurate. And the register value depends on the capacitor. So when you look at the RC value, eventually you will see that it turns out to be a capacitor ratio. So for switch capacitor, in the end, the bandwidth depends on the two capacitor ratio. So the filter can also be accurately designed, the cutoff frequency. Now let's say you don't like switch. I really want to design using the RC. Okay, I really want to design filter like this. What can you do? You have to work out. This guy can vary plus minus 20%. So this guy can also vary plus minus 20%. So the corner is going to get plus minus 40%. So in that case, you have to provide programmable capacitor So you're going to use capacitor like this. So a bunch of them. Okay, to form the final capacitor. To do what? If the capacitor value turns out to be very big, you turn off the capacitor, only keep one of them on. So the capacitor's value becomes smaller. So you can move the cutoff frequency back to the normal position. If your capacitor's value turns out to be too small, you turn on more capacitor so that you can move the cutoff bandwidth back to the normal position. So to tackle for this kind of process variation, component variation, so usually you have to know what kind of variation you expected. So when you design the programmable value, you will try to take that into consideration. So suppose my RC is going to be very plus minus 40%. So let's think. I need to design the capacitor so that if my RC varied by 40%, my capacitor value can down tilt to negative 40% so that they compensate. Or if my RC go negative 40%, my capacitor can go up 40% to compensate it. Okay, so that is how you design using the programmability to counter the process variation. So here give some expression. For resistor, you can see that is related to the length and width. You can all calculate assuming this is length plus delta L or plus minus. Width plus minus delta W. And then you go and manipulate the equation. Eventually you will see delta L, delta W over something. That will give you the mismatch. So you will see that a lot of time you end up having delta L over L, delta W over W. So that gives you a reasoning. Why larger device improve the matching? Because when your L is getting bigger, your W is getting bigger, this delta L, delta W usually is constant. The variation, it doesn't change. It's process dependent. So if it doesn't change, when you have the denominator become bigger and bigger, then this variation only occupies a very small percentage of the overall value. That is how you improve the matching. So same thing for the capacitor, you can do something similar. Here is the question. If you read the textbook, I guarantee you, a lot of textbook will tell you, IC design, you want to guarantee matching. So if you want to match 81K and 44K, what do? Pick a common denominator, a common factor. So 81 and 44, it seems the common factor is 1. Right? So then you lay out unit resistor, 1K, 81 of them. 44K, 44 of them. And then you guarantee these two will match exactly 81 over 44. So most textbooks will teach you to do that. Okay? But that is not the right way. Okay? That is not the right thinking. The right thinking should be like this. 81K, let's rethink. 81K consists of 80K plus 1K. 44K consists of 40K plus 4K. Now, if I can match the 40K, very good. 40K, if matched to 1%, the variation is 400. Right? 1K, you match to 1%, 10 ohm. Right? 400 versus 10 ohm. So even the 1K you don't match very well, is not going to impact you a lot. But 40K you don't match well, is going to impact you a lot. Right? So if you think big, let's do that. Isn't it simpler? 40K, I only need 2 units. 1 unit. If these two match very well, let's say match down to 0.1%, the rest 1K, even you don't match very well, is not going to create a lot of problem. You get the point? So the thinking should be like this. Not think 81K, 81 unit. 44K, 44 unit. Okay? Now, passive device matching. So a lot of time, let's say you want to create register, for example. 1, 2, 3. I want these 3 registers to match to each other. I already lay out identical. These 3 registers are identical. To be frank, they will not match well. Why? Because the second register, they see the neighboring. My left-hand side got something. My right-hand side also get something. Right? So the second devices would see differently from the first devices and the third devices. The first devices only see device on the right-hand side. Third devices only see device on the left-hand side. So they will not be the same. So in IC design, you have to think not only locally, but globally. The device see something similar. If you want to guarantee matching, they should see something exactly the same. Then they will match. So if you really want 1, 2, 3 to match, and you only need 3 devices, but unfortunately, you have to create more than 3 devices. You create the dummy. So you put the dummy on the side, so that the first devices will see both sides. Second devices also see both sides. Third devices also see both sides. So that guarantee the matching is the best. Get the point? Transistor and MOSFET. So for MOSFET, you fabricate the device on the P substrate. So you do it by doing implantation, N+ implantation on the source drain region, and then the P+ implantation on the P substrate. That form the body connection. So MOSFET is a 4-terminal device. You have the gate, drain, source, and body. So from the top figure, it looks something like this. So in the layout, you basically define the poly gate. You define the active region. You define which is the drain, which is the source, and which is the body. Okay, that will define the M+ implantation and P+ implantation. And then you define the opening window where you can make the metal connection. That is how you define the transistor. In cross-sectional, this is exactly what happened. So the red color poly determine underneath the inversion layer can be formed. Okay, source drain. When you implant, although you define the whole active region like a big rectangle, the poly will act as a barrier to stop the implantation. So underneath the gate, the poly gate, you don't get any implantation. So only those that at the side of the poly gate will get implantation. That will help you form the M+ source and drain diffusion region. Same thing for the body. You form another window, another mask layer to form the P+ diffusion. So that is how NMOS device looks like. Now for PMOS, you have to define additional because PMOS sit on top on N-well. Okay? So you have to form an N-well first. And then you fabricate the device on the N-well, within the N-well. PMOS is exactly opposite of NMOS. So the source and drain has to be P+ diffusion region. And the body has to be N+ because it's connected to N-well. Okay? What is the difference between NMOS and PMOS? NMOS sit on top of P substrate. The P substrate is common to all the devices. Think of it like a public swimming pool. Public swimming pool, anybody swimming in the swimming pool will affect all the other person because they share or use the same water. Right? Someone pee, you get affected. So, common substrate. I think I use this example, you understand better, right? Now, what is PMOS? Each PMOS swing in their own bathtub. So they have the bathtub to their own. They are isolated from the other device. So they will not get affected by other device, meaning that you can actually tie the source and the body together. In the PMOS, you can do that. But NMOS cannot. Because if you tie them together, the other device all get affected. So for NMOS, the body all have to connect it to ground. Because the P type semiconductor has to be connected to the lowest potential in the circuit. So the P will not form any forward bias diode to other devices because P is already the lowest. But for PMOS, you don't have this concern. They can short the body and the source together. BJT. So typically the BJT, you fabricate it by using epi layer that form the collector, and then you implant, form a base region, and then implant again, form the emitter region. And then you form the contact on top. So this is actually cross-sectional view, okay? So you form the contact on top to make the emitter base collector connection. You need the buried layer because you can see that the current flow into here have to take a long journey before you go to capacitor. Okay? And this N epi layer usually is not conductive. So very high resistance. That is not good. So the buried layer is high doping. So when the current flow here, they will prefer to go here, or go here, or go here, because lower resistance. And then from here, they just go to the collector. In that case, they can minimize the collector resistance. Okay, so the device performs better. So that is the reason for this buried layer. Now, we seldom do this. So nowadays, when you talk about, let's say you have a pure CMOS devices, you still want a BJT. What can you do? You can see that you can make BJT out of PMOS. So you have this guy, P, okay, and then this is N, and then this is P. So you have a PNP BJT. Can you see that? Now this is not going to be a very good device. Why it is not good? A good BJT, you need to have a very tight control in the base width, which is the separation between the emitter and the collector. You want this guy to be as thin as possible. That will improve the current gain beta to 100 to 200. MOSFET, unfortunately, the base region is formed with N-well. These need to be deep, right? So you don't have very thin base region. So it is not going to give you very good devices, good BJT devices. So the current gain using this kind of inherent parasitic BJT devices, you are going to get current gain of probably between 5 to 10 or 20. The current gain beta, very poor. Now, there is another process called twin well process. You create PMOS using N-well. But I really don't want to swim in the common swimming pool. I want the NMOS to swim in their own bathtub. Can we do that? Yes, you can. So what can you do? You have the P substrate. You have the P substrate. Let's create a deep N-well. So we call it deep N-well. And then we create another P-well. And then we form the devices, MOSFET, NMOS. Okay, this is N plus, this is P plus. So in that case, we have a common swimming pool, a bigger bathtub, a smaller bathtub. Okay, so in that case, the NMOS can be isolated and you can short the body and the source together. Now, the problem, the NMOS characteristic is not as good. Why? Too many implantation, too many impurity. So the mobility will get affected. Okay, compared to directly fabricate the device on the P substrate, the characteristic is better. Okay? So these are the price that you need to pay. Now for this question, I'm going to have a poll again. Which one match better? Let's say you have two transistors. So these two transistors on the left hand side, drain gate source, drain gate source. On the other side, drain gate source, source gate drain. So which one will match better? So let's do a poll. Do you need to scan this again? Please scan this. Done? Yes? All done? Okay. Let's activate the last question. And I present. Wow, some of you already choose. Which one match better? $22 students. I need 38. You just need to flip a coin, right? The head, top, the tail, bottom. All done? 35? The last question, we got 36. Can one more student try? Okay, good, 36. So what is the answer? Majority of you fail. This is not democracy. Majority don't win. Now, why? Why? I know why you like this guy. I know why you like this guy. Because humans are strange. They like something symmetric. Agree? So if you as a human, your left ear here, right ear here, I cut at the middle, symmetric, you look nice. But you put your ear here, this side don't have ear, it doesn't look that nice. Right? But matching is not about symmetry. Matching is the question asking, these two devices, do they track each other well? When we fabricate the devices, think about the process. You are putting the poly on top of the underneath layer, the diffusion. So if, let's say this device here, when you try to place the poly is off. They don't align well. Can you see the problem? This guy, you got drain, you got source. This guy, you got drain, you got source. They still match very well. Am I right? But if you choose this guy becomes source, this guy becomes drain. So one device have very small source, the other device have very big source. They don't match. Get the question? Get the point? Okay? But I'm human. I like symmetric. So what can I do? So I can do this. This is symmetric, am I right? I place it at the mirror. They're mirror, symmetric. It looks nice. Or nowadays, the advanced technology, they don't allow you to rotate the device. The device have to keep at the same orientation. Because you change the device, you change the mobility of the device performance is not good. So advanced process, you have to keep to the same orientation. In that case, what can you do? Make sure you always have even number of fingers. So if you have a single finger, cut it into half, make them parallel. So in that case, like this. Okay, you can join the finger together, so they will still present exactly the same device, as the same single finger device. The good thing, even the poly get shifted, they match, right? And best thing, the symmetric, which align to your human nature. Okay, so these are the two approaches to make matching better. Okay, I don't have any more poll questions. Second lecture, we'll try something. Most model, nowadays we have BSIM model, which is considered to be the de facto standard in device modeling, BSIM. I don't know what is the level now, BSIM 4 or more than BSIM 4, I'm not sure. The problem with BSIM model is that it's very complicated. It has hundreds of parameters just to describe the device. So you can only simulate. You don't really get an intuition how to tweak the parameter to get something. Okay, so that is the problem with BSIM. Now, in design, a lot of people still prefer using square law because it's very intuitive. You increase the W over L, what happened? Okay, you have the overdrive voltage, increase it, what happened? So on and so forth. So square law model, people like to use it because it's very simple and intuitive. But the problem is not accurate. Okay, so how do we reconcile the two? So one possibility is that you still try to treat the model like a square law, and then that gives you a ballpark figure, a ballpark number when you design it. Once you get roughly the ballpark number, you simulate to fine-tune the final design so that you get the actual design. Of course, there are people that don't care about this. They can just use because once you are an experienced designer, you already know. Let's say you have been designing the OM your whole life, 10 years, right? So you roughly know. Differential pair, usually if you use 10 over 0.3, that is good, right? So roughly there, that will give you decent GM. You already know this, so there's no need for you to follow the square law of this thing. You know roughly the device ratio to use. So if I want lower offset, increase the L, but I keep the same ratio. So from 10 to 0.3, maybe it becomes 20 by 0.6. So if you're an experienced designer, you can do that. Okay? If you are not, then my recommendation, you can go back still to the square law and then do some hand calculation. It's not going to be accurate, but it gives you some ballpark figure. And then once you get the ballpark figure, put into the circuit, simulate and fine-tune. Okay? There are another approach that are for computer literate. So those that are very good at programming, what would they do? The EDA tools nowadays are so good. They have optimization program. So you can put down the transistor, specify the L. It changed from 0.2 to 0.6. W, it changed from 10 to 30 in a step of, let's say, 0.5 micron. Okay? And then you let the program run. They will try different combination. And then you set some target. The target is the offset voltage has to be smaller by how much? Okay, the gain has to be bigger by how much? These are the design specs. And then after you set it up, you go home and sleep. Let the program run in the background. Okay, tomorrow you go back to the office, you look at the final result. And then once you get the final result, you see this is the best option, try it again. So this is totally brute force method without any understanding. Let computer decide for you. Okay, there are engineers doing that because they think that if the tool is so smart, why not let the tool take care of it? I'm old school. I prefer you understand what you're doing and then fine-tune. Okay? Device variation. Now, when we fabricate the device, let's say one run. Nowadays, the mask is very costly. It costs maybe 10 million for the advanced process or even more than that. Okay, in the older process, it probably costs a few hundred K to 1 million. Okay, so once you set out the mask, it doesn't mean after you set out the mask, you get the device out, your job is done. Once the mask is done, you might sell the chip 10 millions, 100 millions. Look at the Qualcomm, they sell the cell phone. Apple sell how many cell phones? They will sell how many chips, right? So when they sell their Qualcomm processor, Snapdragon, okay, it doesn't mean one run you get the CPU. This batch, 10,000, I get the 10,000 CPU, okay? Next month, I get another batch, 10,000, right? The 10,000 this month and the 10,000 next month, you cannot guarantee they are the same, right? Because weather might change. The person tuning the process might change. The equipment run at this time is young, run at next month is 1 month older. They might change. The supplier gas quality, let's say the material they are using, the quality might not stay the same month to month. All these things will change. So there is no guarantee this batch will be the same as the other batch. So that is the reason why the foundry provide corner. They cannot categorize, let's say, 100 batch. They fabricate 100 batch and then give you all this data. You'll be going haywire. So what they do is, they already has, let's say, 100 batch. They know that the NMOS can vary from very fast to very slow. So they have these two corners. The PMOS can run very fast to very slow. Another two corners. So combining your NMOS and PMOS in combination, you could end up having either at this corner, fast NMOS, fast PMOS, or this corner, slow NMOS, slow PMOS, or fast NMOS, slow PMOS, slow NMOS, fast PMOS. Right? Once you have these four corners, what the foundry is telling you is that from batch to batch, your device cannot exceed these four corners. So if you run these four corners, the circuit all work, you can guarantee when the chip come back, this is already the worst case. If all these four worst case, it all work. Anything fall in between will work. But beside this four corner design, there also the nominal one, typical corner, the one at the middle, the one that you aim for. So usually you run this 5 process corner to get a feeling how your circuit performance will vary. So when we use the GPDK 045, the first tutorial or homework, you are going to run 5 corner. You are going to see how the device vary. Okay? So what do I mean by fast NMOS, slow NMOS? So fast usually means the current is larger. So therefore it can charge up the capacitor faster. So fast NMOS. So if you know the equation, half mu N COX W over L VGS minus VTH. So what can make the current bigger? Higher mu, higher mobility. Mu N COX, higher COX. But COX depends on what? Depends on the oxide thickness. So smaller oxide thickness. Okay? Threshold voltage. If the threshold voltage becomes smaller, it also becomes faster. So all this is not very well controlled. They will have process variation. So that will contribute to fast NMOS. Now, slow NMOS is exactly opposite. And you know that your chip will not operate at only one temperature. So a lot of time, students run the circuit, they only run at room temperature. Now, for IoT device, usually they consume very low power, maybe milliampere, microampere, that's fine. You know that the junction temperature will not rise very high. So room temperature or slightly higher, usually that works. But if you are designing power amplifier, you are dissipating 1 watt. So that will generate a lot of heat. So when you run the circuit simulation, you should run at 80 degrees Celsius, 100 degrees Celsius. Because this is most likely how the circuit temperature is going to look like. Okay, usually higher temperature, the device performs poorer. Okay, so for commercial product, usually people will run from 0 degree to 100 degree. But for military grade device, you have to run from minus 40 all the way to 150. Okay, why? Because you might be at war at the desert. Temperature is very high, but your circuit fell at 80. It doesn't work. Or you could explore the circuit, explore the environment in the North Pole, very cold. So you have to run the circuit simulation, make sure that you covered all temperature range. In fact, you don't have to talk about all this extreme environment. Automotive is actually very stringent. If you talk about automotive application, look at the car itself. When the car is running, the temperature can get very hot. So usually the testing is very stringent. Why? Because recalling of the car is an expensive process. Let's say the engine, some sensor fail, they have to recall the whole batch of the car. The cost is a lot. So they spend a lot of time making sure the device is very reliable. So you can see automotive, the changes is not very fast. They are very slow changing until Tesla come in, right? But before Tesla, you can see automotive, every year they just introduce something, okay? Let's say reverse sensor, and then tire sensor, and very slow. Then suddenly Tesla comes in, self-driving. Okay, automotive, very slow to change because if anything happens, it's a very costly process. Now, model. Oh, sorry, I forgot to record. So a lot of things will be missing.
Recording in progress.
So good luck. You'll be missing a big chunk of my lecture. You should remind me. I forgot, I'm getting old. Now, model. Now, transistor, usually we design transistor to operate in strong inversion. Okay, strong inversion. So the square law device or linear region, saturation region and linear region apply. So this is what you commonly look at for the equation. One is in square law region, another is in linear region. Now, nowadays, a lot of low power application. You see ridiculous thing. People design amplifier working at 4 nanoampere. It's true. Okay, the ECG amplifier consuming 4 nanowatt. They build the op-amp together with the ADC, all consuming 4 nanowatt. Ridiculous. How they can do that? They operate the device in weak threshold region. Even the wake-up receiver, people are reaching the threshold sub-nanowatt. Sub-nanowatt reaching 400 picowatt. Okay? Of course, whether they are reliable, they can reliably reproduce this thing is another story. But these are the state-of-the-art performance. Okay? So these are the power consumption people are looking at. So why do people go to this extreme? Nanowatt, picowatt. Because they don't want battery. They don't want battery. They want to use just photocell. Okay? Just the light shine on it. It will provide sufficient power to power the circuit. So the circuit can run forever. They don't need battery. So that's why they target for very, very low power. So for this kind of very low power, MOSFET is no longer operating at saturation region or linear region. They're operating at weak threshold region. And the device characteristic is actually very different. It behaves more like BJT. It's exponential behavior. So a lot of students, when they design the circuit, they find this. I keep changing the W over L. Okay? But the GM doesn't change. Why? Because they're already operating at weak inversion. So for weak inversion, for BJT, you know. For BJT, the GM only depend on IC over VT. So you can only change the GM by increasing the current. If you change the W over L, but you keep the same current, the GM never change. So they start scratching the head. The lecturer say that if I increase the W over L, GM should increase. But when your circuit reach subthreshold, using the same current, GM never increase. Okay, so these are the things that you have to pay attention to. Characteristic. So this is the old thing, I didn't bother to update it. So this just gives you an idea. In the old times, I'm using 0.35 micron. So I run it using the device BSIM model. Okay, BSIM model. So for this one, the model is given by TSMC. So you run it. It still looks like a square law, but actually it's not. Okay? The device actually doesn't look like a square law. But as mentioned, we prefer to use square law to calculate. It's easier. So for square law, a very important parameter is I need to find out what is mu n COX. What is my VTH? What is my lambda? So this parameter I need to estimate, right? So how can I do that? So here show an idea. So after you run the characteristic, okay, square law characteristic, you know it's not square law, but you assume it is square law. And then what do? Because you assume it is square law, you can replot this guy, square root ID, okay, after you take the square root. So the square go away, you will see this guy and this guy. You try to compare this guy, square root ID becomes your Y, VGS becomes your X. So this whole thing becomes your C. And in Excel, very easy for you. Let's say all the blue one is actually the data collected or simulated. It's not square. But you can see that over the region, okay, you try to use a linear line to approximate it. It looks pretty nice. And you can use this approach to extract the gradient of this linear line. And then with this linear line, using the gradient, you already design or simulate the device using certain W over L. You can actually figure out mu and COX, right? So same thing, intercept, that will give you the VTHN. Okay, so using this approach, let's say I know that all my circuit, I'm going to use channel length of 45 nanometer. I can characterize this 45 nanometer with certain W over L. And then I use this guy, extract out the mu and COX, lambda, and the VTHN. Then I can use in my calculation. This, by all means, is not accurate. But it gives you a way to start. You get my point? In exam, we already provide you. Assume mu and COX equals to what? Assume lambda n equals to what? Assume VTHN equals to what? But in reality, nobody tell you that. You go to the company, you cannot ask your boss, can you tell me what is mu and COX? I need to calculate, otherwise I cannot do my job. You will get fired, right? So you have to figure out a way, okay, I have to start somewhere. So let's do this simulation, the device simulation. With different channel length, you have to run different simulation and redo. Because different channel length, the mu and COX is going to be different. Okay, you have to do that. Now, non-ideality, MOSFET is a 4-terminal device. So actually, the threshold voltage, if the body and the source are not short together, they will actually modify the body effect using the following equation. So you can see if the VSP equals to 0, then your threshold voltage go back to the nominal one. But if the VSP is not 0, the threshold voltage gets bigger. Okay, but of course, if you introduce VSP equals to negative, then your threshold voltage can be smaller. That is not recommended, because by doing that, you might unintentionally forward bias the diode. So your circuit might have a lower threshold voltage, but you have a lot of leakage because the PN diode is conducting. Okay, so try not to do that. And for short channel device nowadays, the transistor actually doesn't look nice. It has very, very short channel length, so the output resistance is actually very, very small. So it's no longer horizontal. If you learn from 2027, we give you a very nice curve, flat all the way. But short channel device don't look like that. It looks something like this. Okay, it doesn't go horizontal. You actually have significant slope because the output resistance is actually quite small. We can also use the MOSFET devices as a register. So in linear region, remember in linear region, the MOSFET behave like a register. By changing the voltage, you can actually control the variable resistor for the MOSFET device. And the resistor is controlled using the following formula. Again, we assume square law, so this will give you some idea how the resistor change. In reality, you have to simulate and actually get the right resistor value. By using this equation, at least it gives you the ballpark figure. I want to get certain resistor value, how should I set the W over L? So that will give you the ballpark figure. Maybe it's still not accurate, but using the W over L, I try to target for 4K. The equation tell me it can give 4K. but after simulate, it probably only gives me 1K. It's off a lot, but that is a starting point. It's better than I don't know where to start. Anyhow try. Okay, then it will be like trying blindly. You can also use MOSFET as a capacitor. Already tells you MOSFET is a capacitor. Once it turns on, it behaves like a capacitance. So this kind of device is good for supply decoupling cap. Why it is good? Because this advanced device, usually the capacitance is very, very high. It can give you 15 femtofarad per micrometer square. Recently, I ran a simulation. It could even give you up to 18 to 20 per micrometer square. Compared to MIMCAP, 4 femtofarad per micrometer square. That is almost 4 times. So if you use this as a supply decoupling cap, you can save 4 times area. Or think another way, you can get 4 times larger capacitance onto the chip. So using these devices as a capacitor is a good idea. So BJT, exponential behavior, so you all know. So I'm not going to go into the detail. This is the exponential relationship. Usually the turn-on voltage is about 0.7. Okay, the current gain 100 to 200. But remember, if you are using the parasitic BJT device in the CMOS process, you don't get 100 to 200. You only get 10 to 20. Okay, 10 to 20. So usually the BJT is not good, but BJT is good when you try to build band gap. Later we're going to cover band gap. So no choice. This is the only device we can get, so we'll use it to achieve band gap. Not good, but still doable. We also have finite resistance, but it's much better than MOSFET. The early voltage is close to 100 to 200 volt. So now, once you know the device model, we can look at the small signal characteristic. So the good thing about transistor is that they can achieve amplification. How do they do that? Basically, for MOSFET, for example, you change the gate voltage a little bit. The current change a lot, right? So the current is the output current. The voltage is the input voltage. Current divided by output current divided by input voltage. Current divided by voltage, you get conductance. But you are not talking about conductance at the same terminal. You are talking about output current divided by input voltage. So you have to add a word trans in front. So we call it transconductance. How do you obtain this transconductance? Very easy. You already have the IV characteristic. You just have to differentiate. You already know how the current changes with respect to input voltage. We are only interested in small signal behavior. So you take the derivative. How would the current change with respect to the input voltage? So delta I over delta V. So this is how we obtain the GM. We differentiate the output current with respect to the input voltage. So as an example, for MOSFET, we already know ID, output current, is related to the input voltage, VGS, in the square law manner. So if we differentiate delta ID over delta VGS, and we evaluate that at one particular drain current, we will get the GM as the following formula. And one thing you notice is that the GM is proportional to square root of the current. So for MOSFET, you don't expect to get very high GM. You have to pump a lot of current in order to get good GM. Okay? Now, BJT, on the other hand, you do the same thing. Output current is collector current. Input voltage is base emitter voltage. You differentiate. You get this guy. And you see that the GM is directly proportional to the current. Okay? So you can get much higher GM in BJT. Probably something crossed your mind. Just now I mentioned MOSFET in weak inversion or subthreshold region. They actually behave like BJT. So they will provide better GM, right? So why don't we all operate at subthreshold? Why do we still care about the strong inversion? Anyone? You see, GM can be bigger. It's better than square law. BJT tells you that, right? And weak threshold or subthreshold, weak inversion or subthreshold behave like BJT. It means it will give you better GM. So MOSFET, we should operate it as like BJT, give you better GM. Why we don't do that? Anyone? Small current, good. Small current. Weak inversion only work provided the current is small. Subthreshold, current is small. What is the problem with small current? Isn't all of us like small current? What is the problem with small current? Come again? Drive capability or bandwidth. Right? It's proportional to the current. The higher the current, you can operate faster. You can have higher bandwidth. Lower current, bandwidth get limited. So yes, you can have higher GM, but you forgot to take into consideration the frequency of the operation. So it might get better GM, but that only happens at lower frequency. Higher frequency doesn't work. So that is the reason ECG, they do that. What is ECG? How fast does your heart beat? 60 per minute or 1 per second. So what is the frequency range? 100 hertz. Good enough already. Right? So subthreshold is okay. Get the point? So here is the driving point concept versus trans. So in circuit, a lot of time, we borrow the concept. The circuit can be very complicated, but we think. Although it's very complicated, but if I look into it, I have certain voltage, it draws certain current. Then this whole thing just behaves like a register of certain value. You get the point? Why do we want to consider that way? It makes your life simpler. Okay? So it's like your wife nagging at you. Sorry, I'm not. Let's say your wife nagging at you. You know, you need to give me tuition fee, home the weekly allowance, okay, grocery, all these things bother you. But to you, you can simplify the thinking. You just think, this month, I have to give my wife how much? That's it. I don't care what is the detail, right? So it's the same concept, driving point. I look into this guy. I don't care how complicated. I can know. If I apply certain voltage, it draws certain current. Ohm's law tells me voltage divided by current, give me resistor. I don't care whether it's transistor or how complicated it is. A resistor value. It will simplify my analysis. So that is the so-called driving point concept. So driving point concept, you are looking only at one particular terminal. So for example, input terminal or output terminal. That is driving point. How about trans? Trans, look at two different port. Input give, output give. So it's like, I give my daughter tuition fee every month, 1,000. What is the output she's giving me? Did he score A or score B? So that is trans. So for driving point, I don't care. I only look at how much money he draw. But for trans, I'm looking at, I give this amount, what am I expecting at the output? Two different terminals. So using this concept, we can actually analyze the circuit, different amplifier circuit. So for example, in trans, if you are talking about output voltage versus input current, you have trans resistance. If output current versus input voltage, you have trans conductance. If output voltage versus input voltage, you have voltage gain. Output current versus input current, you have current gain. Okay? So you have four different kinds of amplifier. Don't be fooled by this guy, this is actually amplifier. It's just that the quantity is not unitless. Output is current, input is voltage, so transconductance. Output is voltage, input current, transresistance. But these are all amplifier. Now, LF stands for low frequency. So for low frequency, we already analyzed, we know the GM, how the GM looks like. But there is only one parameter, the trans parameter. We also have the driving point parameter, which is the output resistance. So you can see if you apply the voltage at the output, we observe how much current changes at the output. That will give rise to the output resistance, delta ID versus delta VDS, which is 1 over R0. So this gives me output resistance. Now, MOSFET is a 4-terminal devices. So besides changing the gate, we can also change the source body voltage. By changing that, I can also change the current. Not a preferred way, but unintentionally, you can do that. Okay, so in some research paper publication, people run out of idea, so they would come up with a circuit originally controlled with gate. They will say, oh, let's do it using the body. The idea is different, but it's actually poor idea. Okay, because it's never a good control. Okay, so you can see some research publication doing that. Now, the derivation is a bit complicated. Again, we need to find how much current changes with respect to the source body voltage. Delta ID over delta VSB. So we differentiate this current using chain rule with respect to the threshold voltage. And then we further differentiate threshold voltage with respect to VSB. So by doing that, you can obtain the threshold voltage versus VSB as follows. So the GMB can be found as minus GM, which is this guy. And then this guy is basically this thing. Very complicated calculation, but people put in the value. After putting in the value, they find that this part only contribute 20 to 30%. So you get a factor, maybe 0.2 or 0.3. So they round it off, saying, okay, let's take the average, 0.25. So to simplify the calculation, a lot of time, after you calculate the GM, you just ask yourself, is there a body effect? If there's a body effect, the body transconductance value is about negative 1/4 GM. Okay? It's not exact, but it's good enough. Okay? Some of you might complain, am I teaching science, engineering, or am I teaching art subject? It seems like very arbitrarily, anything go. Now remember, square law is not a very good law. It's inaccurate. What we get is just a ballpark figure. So that gives you a starting point, but that doesn't give you the final answer. So to get the final answer, you need to rely on simulation. So don't bother asking, should it be 0.25? Should it be 0.2? Should it be 0.3? Should I actually put in the actual value and see whether it's actually 0.22? Don't bother doing that, because you know eventually square law is not good. But it gives you the starting point. Okay? So the complete hybrid pi low frequency model, low frequency means close to DC. Okay, the capacitor effect not coming yet. So you get two dependent current source. One is GM-VGS, another is GM-B-VSB. Okay? Some students will probably see different model. They will see that, oh, I read somewhere it should be the current source, one going up, one going down. So this is GM. And then this is GMB. So they are confused. They are actually the same. When you use this guy, the GMB is defined as positive. But when you define this guy, the GMB is defined as negative. So in the end, they are the same. Okay? Now, when you consider high frequency, you have to start thinking. The transistor itself actually have parasitic capacitance. So what kind of parasitic capacitance? If you look carefully, this NPN, the source and drain region actually form a diode because this is N and then this is P. So they will form a PN diode. So with PN diode, you have junction capacitance. So you need to estimate the diode area. But the diode area very strange, 3D. So at the bottom, you have a very straight area estimation. But how about the side wall? The side wall also have area. Okay? So for side wall, so usually you look at the BC model, they will give you the CJ, which is referring to the bottom, CJ. And then CJSW, they are referring to the side. Why they separate the two? Because for CJ, you need to know the L and the W to estimate. So it's per unit area. But for the CJSW, you don't know the depth, although you know the L. Right? But the depth, when the foundry fabricate the device, they already know what is the junction depth. So the capacitance for sidewall, the capacitance unit is capacitance per unit length. Okay? So when you calculate, it's different. And you know, for reverse bias, all this diode is reverse bias, so the capacitance is expressed in the following manner. The MJ is the coefficient. Usually it changes between half to 1/3 for diode, depending on the diode characteristic or doping profile. So you can estimate the capacitance accordingly. Now for gate capacitance, so beside the overlapping capacitance, okay, you also have the actual capacitance between the gate and the underneath channel. But this capacitor is connected to both source and drain. So it depends on the transistor operating region. If the transistor is operating at linear region, you have the full channel length set up. So you can assume the capacitor split nicely, half to the source side, half to the drain side. But if you have saturation region, then you actually have pinch off. So all the capacitors appear at the source side. The drain side doesn't have. But the source side doesn't have the full capacitance. You only have 2/3. Okay? So that is how you estimate the capacitance. So again, this is very tedious. It just gives you some understanding where does the capacitor come in. IC designer, it's good for you to understand how the device works. Okay, you don't just design the circuit, you understand the device characteristic. You can actually make something interesting out of it. Okay, I'll share some story later. So after you figure out the CGS, CGD, you just have to ask yourself, where is the capacitor exists? CGD exists between gate and drain, so you just put the capacitor between gate and the drain junction. CGS exists between the gate and source, so you put it there. CSB between source and body, CDB between drain and body. So you can do all these capacitance. Now, low frequency hybrid pi for BJT, very simple, we already know the GM. But for BJT, there is a finite current gain. So when you look into the base, you have finite resistance. And that resistance, using the driving point concept, I apply a VBE. What is the current drawn? Base current, IB. So IB over, VBE over IB. I can do VBE over IC, and then IC over IB. They are the same, right? IC over IB gives you beta. But VBE over IC, we already derived. IC over VBE is actually GM. So that gives you beta over GM. That becomes the input resistance. This is actually undergraduate stuff. And then for the output resistance, use the driving point concept. We apply the output voltage at the collector side and examine the collector current. So the ratio of the two, delta IC over delta VC, that gives you the inverse of output resistance. So usually it's the early voltage divided by the collector current. Sorry, this guy should be IC0. IC0, not ID0. So low frequency, you have the RI, you have the R0, and the GM. Now, you're probably wondering, what is RB, RE, and RC? These are physical resistance. Remember the BJT characteristic of the structure. You have the emitter region, you have the base region, you have the collector region. The current doesn't right away go to the metal. The current has to pass through semiconductor before being collected by the metal, right? So if you look at the structure, emitter resistance probably is negligible because the metal placed right on top. But the base, they have to go sideways before it come out to the base. So there is actually RB from the semiconductor. The collector, we use the buried region, buried layer to actually lower the resistance. Lower doesn't mean zero. It's like the famous slogan, right? Low crime doesn't mean no crime. Right? So low resistance doesn't mean no resistance. So same thing. So RC is there. Now this resistance usually is very small. You don't really care. But at high frequency, it becomes a problem. Okay? So why high frequency becomes a problem? Because at high frequency, you have this capacitor. So this capacitor parallel with RI. At low frequency, this is much smaller than RI, so you don't really care. But at high frequency, your capacitor presents a much smaller impedance, so it's no longer dominated by RI, it's dominated by DC. Now, if your RB is comparable to this capacitor, it becomes a problem. Okay? But this physical resistance can be solved. You can make it smaller. So just now, when we talk about this guy, also the same thing. You might be thinking, in DC, who cares? The gate, look at the infinite resistance. So RG, no matter what value, is negligible. But at high frequency, you start to have this CGS. You have finite impedance. If this RGS now becomes comparable, then whatever the input apply at the gate, when you come to here, they will suffer some drop. A simple resistor divider, right? How to solve this guy? How do you minimize the RG? So, I hit without the pen. Compared to this guy. So, drain, source, drain, source. So, forgive my drawing. This is source and drain. So this is 3W. So each of them is W. Now, on the left-hand side, you actually have 3 transistors in parallel, right? But you connect all the gate together, so it's like, all together, you have 3W add together. So the total width is 3W. It's actually the same as the one on the right-hand side. It's the same. 3W is the same. But if you look at the gate resistance, you have one long thing, the gate resistance is 3R. Agree? This guy, the gate resistance is R, 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 but the 3 devices is in parallel. So what is the total resistance? R over 3. So if you compare the resistor of the two, you reduce by 9 times. You get the point? So that's why for RF, high frequency, you always use short width, multiple finger. You don't try to use long width. So how short is short? Some depend on the frequency. Some people say anything below 10 micron. So if you're more than 10 micron, chop it into different finger. But we work with one industry partner. They share, the engineers share with us, if you are talking about gigahertz range, maybe 5 or 10 gigahertz, try to keep the finger width less than 2 micron. Okay? The shorter, the better. So for BJT, actually the same thing. You can reduce the base resistance by using parallel. So don't use a big area, a very long emitter. So try to chop the emitter into multiple things in parallel. to make the base resistance smaller. Now, the capacitance for BJT, you have PN diode, so you always have junction capacitance. And for collector, base junction is very easy because they are reverse bias. So you only have this junction capacitance. Now, for base emitter, the junction is forward bias. So beside the junction capacitance, you also have the so-called forward capacitance. So how do you estimate the forward capacitance? The principle is this. The BJT operation, you are injecting the electron into the base. How long does it take for the electron to reach the collector junction? So how much charge reach and how much does it take for the charge to reach the collector junction, delta Q over delta T? That will give you collector current. Delta Q over delta T, the rate of the change of the charge is current, right? So delta Q over delta T, you inject the electron into the base, and then it gets swept across the base, reach the collector. So delta Q over delta T, that gives you the collector current. So the delta T, you can approximate it as some time constant. So that gives you the total electron charge injected into the base. Because of the charge neutrality, if I have electron injected into the base, if I don't have hole, the whole region will be negatively charged, right? But that cannot happen. We have to make sure it's neutral. Otherwise, there will be negative charge throughout the base region. How do you have the hole? So the hole is being created because you apply base emitter voltage. The base emitter voltage multiplied by the capacitor, that will give rise to the positive charge. And this charge has to be balanced out with the electron injected into the base. So the principle is actually very similar. Let's say you have capacitor. You already know you have electron at the underneath, right? So you should expect the same positive charge at the top metal because capacitor have to be neutral, right? Positive on one side, negative on one side, balance out. So how do you estimate the total number of charge? If the capacitor is C and the applied voltage is V, Q equals to CV, right? So that is how you obtain this value. And because of charge neutrality, these two have to balance out. So in the end, you get this expression. So this is actually the diffusion capacitance, the diffusion capacitance of the BJT. And usually, if you look at the data sheet, they will give you the transit time. They will give you the GM you can estimate. So from there, you can actually estimate the diffusion capacitance. Diffusion capacitance. So in combination, you have the high frequency model. So C mu is between base and collector. BE is between the base and the emitter, and it consists of two. One is the diffusion capacitance, CB. Another is the junction capacitance, CJE. And then the collector to the substrate, that is basically just here. Okay, substrate. N epi layer, P substrate. They form a PN diode. So again, it's a junction diode capacitance. So they complete the model. What do I say I want to mention just now? I have short-term memory. What did I miss missing just now? I said I want to tell a story. Story about what? Come again?
You never say about.
Yeah, I know, but when I mentioned that, before that, it's related to what topic? I can't remember. Can I recall? No, I cannot recall, so never mind. I forgot. Okay, so that is the first lecture. I already set up a group, so you go and sign up, see which session you want to join. So remember, the EDA2 will be the key in this module. You need to get familiar with the EDA2. The homework project all depend on it. Okay? In the past, we give you the LT Spice. But from this academic year onward, we don't allow LT Spice because we use the GPDK that only exists in Cadence. So with LT Spice, you cannot get any result. Okay? We'll call it a day. By the way, you see that I set out the Zoom. That is not for online lecture. This is only for recording, Zoom recording, so I can share with you. Okay? So don't ask me for the meeting, for the Zoom, because this semester I decided to go face to face, unless there is an outbreak. I hope not. Okay? See you guys.